In this video, we will learn about an artificial intelligence model called Random Forest and take a look at the coding files. First, before explaining the Random Forest model, let's take a look at ensemble learning. The term ensemble comes from French, meaning harmony or unity. Ensemble learning is a technique that combines multiple results to derive a final outcome. In other words, it integrates several base models and uses the majority voting rule or their average to improve prediction accuracy. In this example, out of 5 models, 3 models predicted 1 and 2 models predicted 0. By applying the majority voting rule, we obtain a final prediction of 1. Therefore, even if one model makes a wrong prediction, it is somewhat corrected due to the presence of multiple models. This allows us to obtain a more generalized and robust model. Random Forest is one of the ensemble models. Random Forest uses multiple decision trees as base models. In other words, as shown here, the initial training data is divided into several subsets, and based on that, multiple decision trees are used for prediction. Then, the most frequent prediction from each decision tree model is selected as the final prediction. In the process of determining the final prediction, classification models choose the most frequent value, while regression models use the average value. Furthermore, Random Forest utilizes an algorithm called bagging. Let's take a look at the bagging processing in more detail on the next slide. Bagging is a term that combines bootstrap and aggregating. First, bootstrap is a statistical method of resampling from the initial dataset. It randomly selects samples with replacement, which means duplicates are allowed, and divides them into multiple sets. As shown in this example, from the original dataset consisting of x1 to x6, n datasets of which size is the same as the original dataset are extracted. Since duplicates are allowed during sampling, as shown here, the same data points can be included. Using the multiple training datasets generated through the bootstrap technique, we construct multiple decision tree models and combine their prediction values. This process of combining decision tree models created through bootstrap is called aggregating. The entire process, including bootstrap and aggregating, is referred to as bagging, and the Random Forest model uses this bagging process for predictions. This slide shows a screen for coding Random Forest. The Jupyter Notebook file is available on GitHub, so you can download it and run it yourself. Just like in the previous decision tree model, we import the necessary libraries such as NumPy, Pandas, and TrainTest split library. Then, we load the Excel dataset of Iris. After that, we assign X and Y, and split the data into training and testing datasets in an 8:2 ratio. To build a Random Forest classification model, we import the Random Forest classifier library. As I mentioned in the previous videos, if you encounter an error indicating that the library is not found, you can install it using the pip install command. After importing the library, we create a Random Forest model with 100n underscore estimators and store it in a variable called forest. The number of estimators, denoted by n underscore estimators, represents the number of base models in the Random Forest. In this case, we create a Random Forest consisting of 100 decision tree base models. Next, we train the model using the X-train and Y-train data and evaluate its accuracy. The training data shows a 100% accuracy, indicating that the model has predicted the species correctly. When applied to the testing data, the accuracy is shown to be 0.933, meaning that the model successfully predicts the iris flower species with an accuracy of 93.3%. Furthermore, using the for loop command, we can create a simple code to check whether the actual species and the predicted species match or not. The for loop has a structure of for variable in and is commonly used for repeated executions. Particularly, each data is extracted from the variable a after in, and then assigned to the variable I, and the print command below is repeated. Therefore, the numbers 1, 2, 3, 4, and 5 are printed in order. This can also be utilized to print the multiplication tables, for example. Additionally, the zip command can be used to extract and print one item at a time from variables A and B. By utilizing this, We can show whether the predicted species match the actual species in the dataset used for testing, where we represented the iris species as numbers. Finally, remember to use a colon at the end when using the for loop command.